Welcome to the 18th lecture of our course on quantum mechanics. Last time, we looked at Feynman's sum over histories approach to quantum mechanics. We saw how it applied to quantum electrodynamics, the theory of how electrons and photons interact. And we saw that in QED, quantum electrodynamics, each physical process is represented by a set of Feynman diagrams, and each diagram represents a possible internal history for that process. All the diagrams contribute to the quantum amplitude for the process to occur. We found last time that swarms of virtual particles are present in these diagrams. They come and go unobservably, underneath the limit set by the time-energy uncertainty principle. This means there's kind of creative energy accounting in quantum mechanics. But the energy accounting always passes any audit, any experimental test of the law of conservation of energy. Now this time, we're going to analyze what is going on in so-called empty space. And we'll find that the quantum mechanical answer is quite a lot is going on, and that this fact that there's a lot going on where nothing appears to exist has enormous consequences. So let's start out by supposing we have a simple pendulum, a mass that swings back and forth at the end of a string. Now the simple pendulum has two kinds of energy. There's kinetic energy, it's energy due to its motion, and also potential energy due to its height above the bottom. And as the pendulum swings, it exchanges kinetic and potential energy. At the bottom, when its potential energy is least, its kinetic energy is greatest. Up at the top of its swing, when its potential energy is greatest, its kinetic energy is zero. Now, for a classical pendulum, as I've described, if the pendulum were exactly at rest, exactly at the bottom, then its energy would be zero. But a quantum pendulum can't do this. For a quantum pendulum to have zero energy, it would have to have its uncertainty in position, delta x, and its uncertainty in momentum, delta p, both equal to zero. And the uncertainty principle forbids this. This means that even in the ground state, even in the state of minimum possible energy, the quantum pendulum has 0 point energy. 0 point energy. What is 0 point energy? Well, for a quantum pendulum, the 0 point energy, the energy it must have even in its lowest energy state, happens to be Planck's constant times the frequency of the pendulum divided by 2. And of course, that's just half the size of one quantum of vibrational motion, as Einstein posited it back in his explanation of the heat capacity of solids. So even when the quantum pendulum has its least possible energy, it still has what we might call half of the ghost of one quantum of energy. That's the 0 point energy, the energy it has even when it's at zero, as close to zero energy as a quantum system can be. Okay, could this possibly make any difference? I mean, usually we just measure how the energy changes in a system. We don't really know exactly how much energy is in the system, just how the energy has changed. And this is always present. It's like having a minimum balance of $100 in your bank account. That minimum balance is not something that makes any difference. You can just ignore it and you deal with the amounts that are above $100. And yet, it does have effects. Consider, for example, the strange difficulty we have in freezing helium. Now, almost any substance will freeze, will become a solid if we make it cold enough. And what do we mean by cold? With low temperature close to absolute zero, means that the molecules in the substance have very little heat energy. And heat energy is just disorderly energy of motion. It's an ordinary sort of energy. There's very little of it in something at low temperatures. Now, molecules have something called a van der Waals force. And a way of thinking about the van der Waals force is that molecules are very slightly sticky. They like to stick together. And so if the molecules are moving slowly enough, if the temperature is low enough, then the molecules will stick together and they'll freeze in place. They'll freeze in place. Now, helium atoms have very low mass. They're the next to lightest kind of atom. And they have very weak van der Waals force. And so helium is actually very difficult to condense. It condenses to a liquid close to absolute zero, only 4 degrees above absolute zero. It just barely condenses into a liquid. But even at absolute zero, helium atoms have enough quantum zero-point energy to prevent freezing, to prevent them sticking in place. So instead of a solid, helium forms a superfluid, a state of matter that's very low temperature but can flow. Now, it is possible to freeze helium by imposing very high pressures, and those high pressures sort of make up for the lack of stickiness in the atoms. But at ordinary pressures, no, it's impossible to freeze helium, and zero-point energy is to blame. You see, in quantum mechanics, the ground state is not the state with no energy. The lowest rung on the energy level ladder, to call to mind a picture we use to describe atomic structure, the lowest rung on the energy level ladder may still involve kinetic and potential energy, a kind of irreducible quantum motion. And that's going to have physical effects. All right, so now we're going to turn to a related subject, and that's the physics of empty space. By empty space, I mean it has no particles in it at all. That's got to be the lowest possible energy. Sure, if there are particles, they'll have to have at least the zero-point energy, but if you have no particles, surely that is really empty. That's really no energy at all. Empty space, in short, sounds very boring. And in classical physics, empty space is boring. There is nothing in empty space. But in quantum mechanics, so-called empty space, the vacuum state, has quantum zero-point energy of its own. So let's think about the electromagnetic field. In the electromagnetic field, the energy comes in the form of photons. So if you consider one particular type of light, one particular frequency, and one particular direction, you can have one photon with that direction and frequency, 2 photons, 3 photons. Each photon has an energy which is equal to Planck's constant times the frequency. And so you can have lots of different amounts of energy in that particular type of light. But even with 0 photons, there's still a little leftover electromagnetic energy, a little zero-point energy, that has this frequency and direction in the electromagnetic field. How much zero-point energy? Well, once again, the zero-point energy is equal to Planck's constant times the frequency of the light divided by 2. Even when we take out all the photons we can, even in the vacuum state, there's still half of the ghost of a photon left. So the moral of the story is that the vacuum, the quantum state of no particles at all, is filled with quantum electromagnetic fluctuations, they're called, and they occur at all frequencies. Every frequency and direction has half of the ghost of a photon, even at the lowest energy state. Okay, does all this quantum vacuum energy make a difference? And the answer is, yes, it does. Remember, when we talked about how atoms can interact with light, we said that an atom all by itself, with no light around it, that was in an excited state, could emit a photon. This is called spontaneous emission of a photon. But when you really explore where that spontaneous emission comes from, you find that you can actually regard it as a kind of stimulated emission, but the emission is stimulated by the zero-point fluctuations of the electromagnetic field. It's the energy of the vacuum. That there's always some energy around at a given frequency, and that energy kind of tickles the atom until it emits the photon. Spontaneous emission is actually due to the 0-point energy in the electromagnetic field. Okay. That seems a bit iffy, though. It's kind of an interpretational question. Is there anything more concrete, anything more definite about that tells us that there really is energy in empty space? And the answer is yes. And the person who gave us the answer was a physicist named Hendrik Casimir. Casimir is a Dutch physicist. He worked for both Bohr in Copenhagen and Pauli in Zurich. And then he went to work for industry. He became the director of the Philip Research Laboratories in the Netherlands. But nevertheless, he continued to do research into quantum theory. And in 1948, Casimir, who was already the director of the laboratories, found a way to observe quantum vacuum energy directly. And here's how he reasoned. He said the presence of metal objects actually slightly reduces the way that the electromagnetic field can vibrate. The electromagnetic waves have to fit around the object in some way. If you imagine a metal wall, the electromagnetic waves must vanish at the surface because they can't exist inside the metal. Now, that's only true for low frequencies. Extremely high frequency electromagnetic waves, X-rays and so on, they can pass right through. But at low frequencies, radio waves or even light, the waves can't exist in the metal, and so they have to be zero at the wall. And so we simply do not have electromagnetic waves that don't fit right up against the wall, that don't go to zero at the wall. There are some waves that would otherwise be possible that aren't possible because of the presence of the metal surface. And so the vacuum state is also affected. We don't have half of the ghost of a photon in waves that cannot actually exist. So Casimir showed that the vacuum itself is slightly distorted to fit around a conducting metal object. This sounds pretty weird, but in fact, you can propose a definite experiment. Imagine you have two parallel metal plates. Now, between the plates, we can only have waves that fit exactly between the plates. And this is like the standing waves on a stretched piano wire that we discussed way back in Lecture 5. Only certain wavelengths, only certain frequencies could fit between the two fixed ends of the piano wire. In a similar way, only waves that exactly fit between the two parallel metal plates are allowed. All the rest of them simply don't exist. And so that means that between the metal plates, even if there are no photons at all, the kinds of vacuum fluctuations that there might be between the plates is a little bit less than it would be if the plates were not there. So what does that mean? That means that there will be less vacuum energy. There'll actually be less nothing between the two plates than there would be outside them. The vacuum energy, if you think of it as zero, well, it's actually a little less than zero between the two plates because there are fewer ways to put waves between the plates, and therefore fewer waves that have half of the ghost of a photon in them in the vacuum. And so if there's if there's a little bit less energy between the plates, that leads to a kind of negative pressure between the plates, a tiny attractive force between the plates. So Casimir predicted that due to the quantum vacuum, these fluctuating electromagnetic fields, these ghostly half photons that are present as 0-point energy, even when no real photons are present, there's an attraction between parallel metal plates. That's called the Casimir effect. And the Casimir effect was soon detected, not long after he worked it out. It was soon detected experimentally. Accurate measurements of the Casimir effect had to wait for the 1990s, though. And that's kind of an interesting story. Why the wait? Well, this force that we're talking about is really, really tiny unless the plates are extremely close together. And if the plates are this close together, it's really hard to make the plates exactly parallel. No matter what you do, one end of the plate will be a little closer than the other end of the plate, and that's really hard to predict and to measure. And so because you can't make the plates parallel enough, then it's hard to get a good quantitative measurement of the effect. The better experiments that they've done more recently involve a flat plate and a sphere, and it doesn't matter what angle the sphere is at. You don't have to arrange that very precisely. The theory of the Casimir effect between a flat plate and a sphere is a little bit more complex, but the experiment is much easier to do. And so now we have very accurate measurements of the Casimir effect, and it is just as Casimir proposed back in 1948. So, the moral of the story, the Casimir effect is real. It's a force between objects that is entirely due to the properties of empty space, to the energy that's present in the quantum vacuum. Well, that's kind of neat. There's a force due to the energy of empty space. Could we use this force as a source of power? Could we extract useful energy from the vacuum and solve all of our industrial energy problems? This is an idea that sometimes comes up because getting something from nothing sounds pretty good. So let's imagine the Casimir engine. In the Casimir engine, we bring two metal plates really close to each other, and there's an attractive force between them, and so we let this attractive force between them pull, lift weights, or do some useful work, or generate electricity. As we allow the plates to come together, we allow that force to do some useful work. Now, the force is pretty weak, but in fact, we can actually get energy out of it until the plates actually come together and touch. Well, so we'd like to use the Casimir engine again, but to pry the plates apart would amount to rebuilding the vacuum in between, and we'll have to put back in just as much energy as we extracted. So the moral of the story is we can get a little something out of nothing, but only up to a point. The Casimir engine actually uses up the available vacuum energy as we draw the plates together. So the Casimir engine will not solve all our energy needs. Too bad. But that doesn't mean that the vacuum energy is not important. In fact, it's tremendously important. It may be cosmically important. As you may know, the universe is expanding. All of the galaxies in the universe are moving apart from each other. It's as if space itself is expanding. That's really the right way to think about it. And this is all an after effect of the Big Bang. The Big Bang was a time when the universe was very small, whatever that means, very dense and hot. The matter in the universe was very close together, and then the universe expanded rapidly. And the Big Bang happened about 13 billion years ago. Now, the ordinary gravity between the galaxies tells us that the expansion of the universe should slow down over time because the galaxies are pulling on each other. The expansion slows as the universe expands. And that has led over the decades to an interesting question. The question is whether the universe will expand forever, its expansion will outrun gravity, or whether the gravity will be enough to cause the universe to come to a stop and maybe collapse back in on itself at some distant future date. And so that's a question that cosmologists have been pondering and making observations to answer for some time. And then in 1998, the cosmologists announced a totally astounding discovery. When you look out into distant space, billions of light years away, you're also looking back in time because it takes light time to travel to you. When you look very far out in space, you're looking at how the universe was at an earlier phase of the universe's history. And so when you do measurements very precisely, you find that not only is the cosmos expanding, it's actually expanding at an increasing rate. It's expanding faster and faster. The expansion of the universe is accelerating. So it certainly looks like it's going to expand forever, because it's not only not slowing down enough, it's not slowing down at all. It's actually speeding up. Why? Why is the universe speeding up as it expands? And the short answer is that cosmologists don't know. But they have a name for the cause of this, a name for what they don't know. And that name is dark energy. Now, it's called dark energy for a very good reason. It's called dark because we actually do not see it directly. Whatever it is, it's not emitting light. We don't see it in our ordinary telescopes. So it's dark. And it's called dark energy to distinguish it from dark matter, which is a kind of matter of an unknown type, which is also present. We can see its gravitational effects, but it has a different effect on the universe. There's something called dark matter, but this is dark energy. And this dark energy is really important. In fact, if you want to make a rough inventory of the contents of the universe, no more than 5% of the stuff in the universe is ordinary matter, the stuff that's made of atoms. This no more than 5% includes all the stars, all the planets, all the gas clouds, all of that stuff that we're familiar with. That's less than 5% of the stuff in the universe. About 25% of the stuff in the universe is dark matter, whatever that is. And there are some interesting proposals about what that is, but nobody knows for sure. 25% of the stuff in the universe is this dark matter. We're not quite sure what it is. But that leaves 70% of the stuff in the universe, which is dark energy. And it's the dark energy that causes cosmic acceleration, and it's the dark energy that dominates. Most of everything is dark energy. That's actually a very astounding result of modern cosmology. At least 95% of the universe is stuff that is unknown to us. We don't know what it is, what its nature is. Which means, of course, from the point of view of a scientist, these are great days for cosmology, because there are some of the most important discoveries yet to be made. Now, interestingly, Einstein himself suggested something like dark energy in his early work on relativity and cosmology. You see, Einstein thought that the universe was static over time, that it neither expanded nor contracted over time. It's sort of the common sense view in his day. And so, to make his model of the universe work out, he needed an outward push to counter the effect of gravity, which would cause the universe to collapse. He found that if there wasn't such a push, then the universe would have to either be expanding or contracting. It couldn't be static. Later on, it was discovered that the universe was actually expanding. And Einstein said, oh, this extra stuff that I put into the universe, this kind of dark energy that I included in the universe, that was my greatest mistake, he said. But nowadays, Einstein's greatest mistake is coming back into fashion. Einstein's dark energy, what he called his cosmological constant, is a kind of energy that is present even in otherwise empty space. As the universe expands, there's actually more of it. Now, that may make us worry. You say, well, if there's more of it, where does it come from? Where does all this energy come from? And with your permission, I'm going to duck the question. The law of conservation of energy is extremely tricky to apply to the universe as a whole. Suffice it to say, it does make sense mathematically, although it is very strange to express it in English. So, what's the dark energy? What is this energy of empty space? And a leading hypothesis is that dark energy is the same as the quantum vacuum energy, as the zero-point energy that the electromagnetic field and other quantum fields have, even when there are no quanta, even when there are no photons, for example. The quantum vacuum energy is the dark energy. And as space expands, more dark energy appears, and that drives the expansion faster. And that's why the expansion of the universe is accelerating. In other words, quantum vacuum energy may have cosmic implications. Now, I have to confess, there is a major difficulty with this theory. If you plug in the obvious numbers, if you do the calculations, then you find that there should be a lot of vacuum energy. A lot of vacuum energy. I mean, there's half of the ghost of a photon of every frequency and direction, no matter how high the frequency. Talk about your ultraviolet catastrophe. There's huge amounts of vacuum energy in empty space at these extremely high frequencies, because there are lots and lots of ways that the light waves could be going. And every one of those waves has half of the ghost of a photon in it. So the amount of vacuum energy that you calculate is much, much, much too large to be the dark energy, which is, after all, pretty sparsely distributed in the universe. It's only a couple of dozen times more prevalent than matter, and the universe is mostly empty space, mostly spaces between the atoms. The atoms are very sparse in the universe as a whole. So there's way too much quantum vacuum energy to account for the dark energy. Now, most people would say that it does make sense for the vacuum energy to have no effect at all, that the vacuum energy somehow doesn't count when you're considering how the universe behaves, you're considering gravity. That it's kind of renormalized away, like we talked about last time, where you have something which appears to be infinite, but there are other infinities that cancel it, and it's not really, it doesn't really make any contributions. But that's very difficult to make work out. It's easy to imagine that the vacuum energy has a huge effect. It's easy to imagine that the vacuum energy has zero effect. Both of those make mathematical sense. It's very hard to imagine that the vacuum energy has only a small non-zero effect, which is what the dark energy in the cosmos is. So the dark energy might not be quantum vacuum energy after all. It's hard to say. We just don't know right now. However, cosmologists believe that immediately after the Big Bang, there was a short period in the universe's history, a small fraction of a second, where there was a super fast expansion of the universe called cosmic inflation. This cosmic inflation hypothesis explains a lot about the distribution of matter and energy in the universe. And this period of cosmic inflation may well have been driven by quantum vacuum energy in the early universe. And that would have been very, very important indeed in the formation of the universe we see. Okay, we've gone pretty far to the origins of the universe and the reason why it's expanding. And what we've been telling is a very fascinating and complex story. It's a story that is still unfinished. It's the story of how nothing at all in the quantum sense can lead to stupendous implications for the physics of the world. Fascinating story, but I'm afraid we're going to have to leave it there. With the physics of the quantum vacuum, we've completed our so-called sightseeing tour of the quantum world. We've completed section 3 of this course. And looking back on it with the eyes of a quantum physicist, I have to tell you, we've skipped almost everything. But at least we saw bosons and fermions and the distinction between them, the most important minus sign in the world. And we've seen quantum entanglement. We've seen the EPR argument and Bell's theorem that told us such a startling story about the nature of physical reality. We saw Feynman's quantum mechanics. We saw quantum electrodynamics and this whole strange business of virtual particles. And we saw the physics of the vacuum, the very strange and important quantum physics of so-called empty space. Next, we're going to spend a few lectures discussing a contemporary topic in quantum research. This will be section 4 of our course on quantum information and quantum computing. We're going to be asking how we can use quantum physics to store and transmit and process information. We're going to ask, what does quantum mechanics tell us about the physical nature of information? And what does information tell us about the nature of quantum mechanics. I'm very fascinated by this. This is my own field of research. And this subject, which is a very new one, has disclosed a lot of amazing things about the quantum world. So there are some good stories to tell. We begin quantum information next time. I'll see you then.